So starting off here, the essential question of the day, by the way, is how do graphs and equations communicate key features of exponential growth and exponential decay functions? So the first thing we're going to do is identify key features of exponential functions. Now, just like with polynomials, the values that are within the particular functions tell you things about the functions, whether or not you actually know the numbers. And then if you know the numbers, you know even more. So it says right here, what are the key features of each function? Include the domain, possible values of x, include the range, possible values of y, any intercepts, x or y intercepts, any potential asymptotes, and the end behavior. What's it doing at each end? So there's kind of a lot that we're going to be writing about these, but the look of the graph, the way the equation is written, values of x and y, those are all going to give us clues as to what's happening. So an exponential function is any function of the form f of x equals a times b to the x power, where a and b are constant values, with a not equal to 0, because if a was equal to 0, the whole thing would just be 0. It would not increase at all. B needs to be greater than 0, and b can also not equal 1. B needs to be greater than 0 because if it's less than 0, the function gets really weird, which we're not going to be dealing with, I don't think, at all in this unit, at least, and maybe not even in the school year. And then if b is equal to 1, then exponents don't really matter, because if this value here, if the base value with your exponent is 1, no matter how many degrees you take that to an exponent, it's still going to be 1. So, which means it's not going to end up increasing at all. It's just going to be flat. So that's why there are constraints on the values of a and b. So everything that we see, a isn't going to be equal to 0. B will be greater than 0, but it also will not equal 1. So for our first function, we've got f of x is equal to 2 to the x power. This is the graph. This is the table of values. And it says over here, for the function f, b is equal to 2, because the base value, the value that has the exponent, is the value of b. X is the exponent. The value that has the exponent is 2. Therefore, b is equal to 2. So anytime you're figuring this out, whichever x is going to be your exponent, whatever number is taken to the power of x, that is your value of b. There's nothing mentioned about a here. What is our value of a? So look at the form of the function, a times b to the x power. What does a equal? 1. Yeah, a is 1. There's nothing on the front end of this multiplying by the 2 to the x power. So that means that if there was a value of a, we could have written this as 1 times 2 to the x power. So that means that a is 1. That's not part of this problem, but it's something that's good to know. So because b is greater than 1, the y values of the function increase. If b is greater than 1, the y values will increase. Now, it also says that in general, b has to be greater than 0. So that means there's only really 2 potential options here. If b is greater than 1, or if b is less than 1, but still greater than 0. Those are kind of the only 2 options for exponential functions. This is one where b is greater than 1. The y values increase. For any function where you have an exponential, the y-intercept is a. The y-intercept is equal to a because b to the 0 power is equal to 1. We just said a was equal to 1. B to the 0 power here is also equal to 1. So the y-intercept is a, 1, because b to the 0 is 1. Anything to the 0 power is 1. All right. So on a particular problem like this, if we look here, we're supposed to state the domain, the range, the y-intercept, the x-intercept, asymptotes, and end behavior. So a lot of description going on. This one goes negative and positive forever on the x-axis. Therefore, the domain is all real numbers. The range. I generally don't write things like this. If I was writing this like this, I just would have said, y is greater than 0. That's how I would have written my range. Y is greater than 0. This just says for all values of y, y is greater than 0. But most of the time, I just write an inequality. In that case, it means the same thing. For the domain, it's just all real numbers, because it goes negative forever on the x-axis, and it will continue to go positive forever on the x-axis as well. For the range, it's y is greater than 0. Yeah. So any value for y, so long as it's greater than 0, because there's an asymptote at 0, and we'll talk about that in a second. Below zero is real numbers too. Because real numbers are numbers that don't have I, non-imaginary values. So positive, negative, irrational, fractions, all that is a real number. So we're specifying that they are real numbers so long as that they are greater than zero. Yeah, they can't be negative. The y-intercept is at 1 because that's where it crosses the y-axis. The y-axis will always, the y-intercept will always happen, by the way, when x is equal to 0.
Wait, why isn't the range greater than
Because it goes beneath 1. It doesn't start at 1 and then it doesn't level off at 1. It levels off at 0. Yeah. We will see examples of things leveling off at 1 today, but it'll be an alteration to that parent function. Let's see. We have an asymptote at the x-axis. Or if you want to, you could say x-axis or y equals 0. Either way. If you want to write the equation of the line would be y equals 0, or you can just say it's the x-axis. Either way is fine. And then with end behavior, this is stuff that you talked about in chapter 3 with polynomial functions when you were graphing polynomials, you know, like as x goes to negative infinity, what's happening to y? So over here, as x goes to negative infinity, y is approaching 0. So as the graph goes this way, the y value is getting closer and closer to 0. As x goes this way, the y value is skyrocketing and it will have no end to it. So that's why it says it's going to infinity. So as x goes to positive infinity forever, y also goes to positive infinity forever. As x goes to negative infinity forever, y is getting closer and closer to 0, but will not actually ever reach 0, which is also the same thing as having an asymptote at that point. So those two things right here are basically saying the same thing, but in a slightly different way. Any questions about the description here before we move on? Everything that we've seen here is stuff that you've talked about so far this year, but I think it's been a little while since we've discussed all of those things at the same time. So let's have ourselves a look at the next one. This time, we have 5 times 1/2 to the power of x. So this time we have an a value of 5. We have a b value of 1/2. And so what that ends up looking like here is what's happening to the y values as x increase. What are the y values doing? They're decreasing. And the reason for that, it tells us right here, for the function g, b is equal to 1/2. Since b is less than 1, the y values of the function decrease. So if your base value, the base value next to your exponent, if that's greater than 1, the y values will increase as x increases. If the base value b is less than 1, but still greater than 0, so basically a fraction between 0 and 1, that means that as x increases, your y values will decrease. It's exponential decay. I'm sure you've seen this in science before. So exponential growth versus exponential decay. So this would be like, you know, if you're calculating a radioactive half-life, that would be exponential decay. If you're talking about population, oftentimes that's exponential growth. So if you ever talked about those in like social studies or science, that's what we're dealing with here as well. But we're looking more at the theory as opposed to, you know, the utilization, but we will see some real life examples. Okay, the question off to the side here says, as x increases, this fraction is going to continue to get smaller and smaller. Will it ever reach 0? No. Has anybody talked about radioactive half-life in science? No? Radioactivity basically means like a half-life means that's the time it takes for something to lose half of its radioactivity of a radioactive element. So like after a certain amount of years, it loses half its radioactivity. After a certain amount of years, it loses half of that remaining radioactivity and so forth, which means theoretically, you can never get to a radioactive level of nothing because it's always being cut in half. And if you're going to cut something in half, you have to have something to begin with. And so that's the same idea here. The fraction is getting smaller and smaller, but it's never actually going to reach 0 because if a fraction is decreasing right here by half each time, then it will always have half of whatever was left to begin with, which means you can take half of that, and then half of that, and then half of that. It'll just get smaller and smaller and smaller until it gets infinitely close to 0, but never actually reaches 0. So here we go. Domain, all real numbers, because it goes left forever and it goes right forever. The range, it's the same as the last problem. y is greater than 0. Every value of y is greater than 0 because it'll never actually get down to 0. The y-intercept this time is 5. Do you notice a relationship between the value of a and the y-intercept? What was the value of a on this part? On the first one? The a value is 1. What was the y-intercept? 1. Here, a value is 5. What's the y-intercept? 5. Okay, so far we can say that a is equal to the y-intercept. It is. And the reason it is because if you take the base value to the power of 0, you get 1, which means you would multiply 1 by whatever a is, which is just going to be the value of a. So a is the y-intercept. We have an asymptote, again, at the y-axis, which is the same as y equals 0. And this time, our end behavior is opposite of what it was the first time. This time, as x goes to negative infinity, y goes to positive infinity, because it goes up forever as you go left. And as you go right, it doesn't go down forever, it just gets closer and closer to 0. So as x goes to positive infinity, y approaches 0. All right. Any questions so far? No? All right. Let's have ourselves a quick little look at a function. Actually, let's do some writing before we actually graph this thing. So we are going to graph it. So let's get our values set up here. There's our y-axis. Let's talk about this real quick. Domain. What do you think domain is going to be for this graph? All real numbers. Okay. So the domain is going to be, I'm just going to use the all real numbers symbol, the double vertical line, capital R. What's that? So if it's exponential growth or decay, the domain is going to be all real numbers because there isn't going to be a limitation on what x can equal. So it'll just be all real numbers basically for everything that we're using. The range, I'm going to hold off on that for a second. It is y is greater than 0, just like the last ones. But we'll learn kind of why that is in just a minute. So, all right, let's put that in there. Range, y is greater than 0. What's the y-intercept? Yeah, y-intercept is 4. And because the range is y is greater than 0, that means we have an asymptote at y equals 0. Or if you want to say the x-axis, that's fine. And then the end behavior, I'm just going to write ends. So the ends, as x goes to negative infinity, who can tell me what's going on with y? Y goes to positive infinity. How do we know that? Yeah, the value of b, our base value for the exponent is less than 1, but still greater than 0, which means it's exponential decay. Because the b value is less than 1, but still greater than 0, it's decreasing as it comes in. So that means as x goes to the negative side, y is going to increase forever. All right. So as x goes to positive infinity, what happens to y? It approaches 0. All right. So before you even graph an exponential growth or decay function, you can actually know all of those things. You don't actually have to graph it to know those things. Now, the things that we'd be a little bit unsure about would be the range and the asymptote behavior, but I think on the next page, we'll get some more detail on that. But let's take a look at the graph. And I'm just going to type in, so we got 4 and then 0.5 to the power of x. And then I'm not even going to look at the graph. I'm just going to go to the table of values. And let's see, x-axis, I'm going to put this at the bottom of my graph, not in the middle. The x-axis will go at the bottom. And then in terms of what I can fit on here, it looks like I need to start at -1. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be right here. There's -1, 8. 0, 4, right here. 1, 2, 2, 1. 3 is 1/2. 4 is 0.25. 5 is 0.125, which makes sense because every time we go 1 to the right, the value of y is getting cut in half because that's the value of b. Which means it's being divided by 2 every single time. That's what happens to our function every single time with a y-intercept of 4. So we can just go ahead and drop this on down. And it'll curve through and it'll level off and it'll approach 0, but never actually reach 0. There we go. Looks super similar to the previous function. It actually should look exactly the same as the previous function. It's just moved down 1 unit because the y-intercept is down, but the value b is the same as the previous problem we did. All right. So far, I don't think we've done anything new. Every single thing that we've done so far is stuff that you've done before. Maybe not all in the same problem, but it's all stuff you've done previously. Any questions right now? Does anybody need more time on this? Flip the page. All right. Now, we get to talk more about a on this page, the value of a, because the value of a doesn't just determine the y-intercept. The value of a also determines which direction our exponential growth or decay ends up going. So, right here, example 2 says to graph each exponential function, which they're already graphed. Describe the graph in terms of the transformations of the parent function f of x equals 3 to the x power. This is the one that we saw on the front page with the warm-up. Here we go. How do the asymptote and the y-intercept of the given function compare to the asymptote and intercept of the parent function? Here we go. Everybody take a look. So, listen up, guys. Parent function, y equals 3 to the x power. That's this one right here. There's f. That's f of x. G of x is y equals -3 to the x power. That's this one right here. So, the y-intercept went from +1 to -1 because a went from +1 to -1. A is now -1. So what that tells us here is that b, listen up, b is not -3. B is still 3. That's an important thing to know here. Take a look. B does not equal -3. It's just like, it's actually like when we had, go and write this down real quick. When we had quadratic functions, where you had y equals ax squared plus bx plus c, when we're dealing with quadratics. And if you had a function that said y equals -3x squared plus 2x plus 4, something like that. This one did have a negative value of a, but the negative meant that there was a reflection across the x-axis. Now, there's a little bit of a difference between how we calculate this stuff, but at the same time, a would be negative, but it's the negative that ends up causing the reflection. Same thing here. The negative causes the reflection here. But b is still equal to 3. A is now -1 because of the negative right here. And that's an important distinction because this is still exponential growth. It's just happening upside down. Because it's still getting, the number is still getting larger and larger and larger. It's just getting larger in the negative direction as opposed to the positive direction. Exponential decay means it's leveling out as it decreases. This is not leveling out as it decreases. It is increasing in its negativity as x increases, if that makes sense. So off to the side, let's write right here. Let's write a equals -1, b equals 3. Just so we know that a negative does not, in this case, does not get included with our value b. What would make, actually, let me ask you this. What could we write in here that would actually make b equal -3? Yes, parentheses. And the other reason why we know, what's the other reason why we know that b isn't equal to -3? It would be doing something really weird, and in order to be exponential growth or decay, b has to be greater than 0. That is a rule that we saw on the previous page. Anything with exponential growth or decay, the value of b must be greater than 0, which means here, b cannot equal -3 because it has to be greater than 0, which means that a must be the negative, which is -1. Good? All right. So moving on. You may confuse the reflection across the axes. Recall that the y value, if the y value is multiplied by -1, as in this particular case here, the reflection is across the x-axis. Each y value is replaced by its opposite, which means that if this was like -3 to the power of x plus 2, that means that we'd end up having it flip over and the negative would have been applied to more than one thing. Okay, so down here, the y-intercept moves from a to -a because a is now -1. The asymptote of the function, though, doesn't change. It's still the same because as x goes to -infinity, y still goes to 0, even though it's upside down. You'll see something kind of similar over here. Our asymptote does change on this one, and this is what happens if we introduce a vertical shift. By the way, you're going to notice a lot of similar variables because anytime we dealt with vertical shifts in previous units, what was that basic variable called? It's right here. It's k. Anytime we move things up or down, it was moved up or down by a value of k. We're still calling it k. So h of x is equal to 3 to the x power minus 4. So a is equal to 1, b is equal to 3, and we have a constant value of k, which is -4. So that means it's 3 to the x power, but it's been shifted down 4 units. So we can see here, this is the, whatever the y value is, f of x is the same thing as y. So for whatever y is, take away 4 from it. So if you look at the graph, we go from a y-intercept of 1, we move that down 4 units. It's now a y-intercept of -3, which changes the asymptote because the asymptote also gets moved down 4 units. So it was 0, now it's -4. So this is something right here as well. An asymptote is going to happen at y equals k. Whatever k is, if there's a plus or minus afterwards, after the value of b to the x, if there's a plus or minus after that, that's where your asymptote is going to be. If there isn't a plus or minus, you have an asymptote at 0. If there's a plus, it's going to be up. If there's a minus, it's going to be moved down. This one happens to be at -4. So we're not even going to graph these next ones. We're just going to talk about what the graphs look like. Actually, we should probably look at A. I think that would be a good idea because we haven't actually seen this yet.
We have to take the asymptote.
You have to say where they are? Yeah. So this one says, how do the asymptote and the y-intercept of the function compare to the parent function 5 to the x power? So take a look here. This is going to be a little bit odd. What do you think is going to happen to this one? So if it was like 5 to the x and then it was +3, but the +3 wasn't part of the exponent, then yes, it would go up 3. Let's type this in and see what happens. Let's type them both in and let's see what happens. So we're going to have 5 to the power of x. So there's our parent function. And let's go to 5 to the x plus 3. And let's see what happens. Any guesses? There's our parent function. There you go. It went to the left 3. Good. How did you kind of figure that out? Yeah. Anytime you make an adjustment to the x value, that is a horizontal shift. Remember that? If you change anything that's with the x value, that's going to mean a horizontal shift of some kind, or a stretch, or a reflection. Anything that's done with the y values, that's going to be a vertical shift, or stretch, or reflection. So What do you think is going to happen? Actually, let's just talk about this one. So this is going to be asymptote is unaffected, right? So for A, let's see. Asymptote is the same. And then what about the y-intercept? So this says asymptote is the same. Yeah. The asymptote is the same. What about the y-intercept? It was 1. What do you think it is now? The y-intercept. Because the asymptote doesn't change. It still levels out at 0.
What do you want to do that? That's 5 to 5.
So how many factors of 5 was x increased by? 3. Right? So the asymptote used to be at 1 because, well, that's when x was 0, right? Still, it's the same thing when x is 0. So previously, if x is 0 here, 5 to the 0 power is 1. It's still going to be when x is 0, but now it's 0 plus 3, which is 3, which is 5 to the 3rd power. So where's our y-intercept? 125. Because that's 5 cubed. Whenever x is 0, you have your y-intercept. So we're still going to plug in 0 for x. 0 plus 3 is 3. 5 to the 3rd power, 5 cubed, 5 times 5 times 5, 125. So the y-intercept increases by 124, but the asymptote stays the same. Over here, let's see. What do you think a negative exponent of x is going to do? Which way? X-axis was upside down. The y-axis, yeah, it's going to do this. So it is going to go from, it'll be going up like this to flipping it around. What's that? Yeah, so if we go back here and we type in 5 to the negative x, delete, delete, and then plus 6. Here comes the parent function, and then it should just be things flipped around, but also moved up 6. So it should look exponential decay. There it is. So it's going to flip around, and it'll be moved up 6 spots. Because the negative is the negative with the exponent here is a reflection across the y-axis. That's a horizontal reflection. And then it's also been moved up 6. But we're not going to write that. What we're going to write is, how do the asymptote and the y-intercept change? So when x is equal to 0, actually, let's start with the asymptote, b. So the asymptote has been moved up what? Yeah. Has been moved up 6, so now it is y equals 6. That's where our asymptote is now. The y-intercept, what's happened to the y-intercept? What is the y-intercept? Plug in 0 for x. 5 to the 0 power is 1. 1 plus 6 is. So the y-intercept has been moved up 6. 2. Y equals 7. It was at a location of y equals 1, but because it went up 6, everything just moved up 6. Yes, it's been flipped, it's been reflected across the y-axis, but the y-axis reflection didn't have any effect on either the asymptote or the y-intercept. That reflection didn't change anything. Also, the reflection it changed the y-intercept here because it flipped it upside down. So if you have a vertical reflection, it changes the y-intercept, but if you have a horizontal reflection by itself doesn't change anything in terms of asymptote or y-intercept. It changes the fact that it looks like decay instead of growth, but doesn't change anything else. All right, questions here before we move on? Okay. Not many calculations going on, just a lot of identification today until we get to this page. So here we go. Population. The population of a large city was about 4.6 million people in the year 2020 and grew at a rate of 1.3% for the next 4 years. All right, then it says, what exponential function models the population of the city over that 4-year period? So it says, first of all, compute the population for the first few years to look at a pattern. So if something is increasing, we'll go ahead and do this on our calculators. If something is increasing at a rate of 1.3% for the next 4 years, that would be, first of all, how many million? 4.6. So 4.6. How could we figure out a 1.3% increase? Listen up. What would we multiply 4.6 by to represent a 1.3% increase? What's that? 0.013, because percentages as decimals, right, are not written the same. So 1.3% would be 0.013. What's that? Because that's how percentages are written as decimals. Okay. Like 50% is 0.5, right? Yeah. So 1.3% would be 0.013. 5% would be 0.05, so forth. Okay. Now, if we wanted to know how many people it increased by, we would multiply by 0.013. But if we wanted to know the new population, we would take the original 100% and then add 1.3% to that. So basically, the next year would be 101.3% of the original. Does that make sense? Okay. So instead of multiplying by 0.013, it says right here, multiply by 1.013. Because you're taking the original amount, that's the 1, and then you're adding on the 1.3% as well. So we're just putting that all together in one number. So times, multiply that by 1.013, which ends up being 4.6598 million people. Or 4,659,800 people. If you actually expand that out and talk about the number. So this is what happens after 1 year. If you want to know what happens after 2 years, just hit times, multiply that by 1.013. After the year after, 4.723774 million. And you're actually going to see these, these numbers off to the side here. And what ends up happening, though, is if you end up compounding the growth rate, that growth rate ends up turning into, because you're multiplying it by itself over and over and over, you could do this over and over and over, which would give you the same answer, but you can write it as exponential growth, because if you start with an initial population of 4.6 million people, and it's growing at a rate of 1.3% per year, meaning the original 100% of the folks plus an additional 1.3% on top of that, taken to an exponent for the number of years, you can figure out what the population is going to be a certain amount of years down the road. So here's our function. The population is going to equal the initial population, there's our value of A, multiplied by the growth factor. This is our number. Hey, by the way, is this number greater than 1? Yeah, B is greater than 1. Therefore, the population is increasing. So this is what we just saw. This is This is f of x equals a times b to the x power. It's the same function. We're just using it to talk about population growth. So a is the population that we started with. Our growth factor, because it's growing, that means the number has to be greater than 1. If it was a decay factor, this number would be less than 1, but still greater than 0. And then t is the number of years since 2020. That's our exponent x. So what will the population be in 2050? Let's write the function. So P equals 4.6 times 1.013. What's our value of x? Pay close attention here. What's our value of x? What is time? 30. Why? T represents the years since 2020. If we're calculating the population in 2050, that's 30 years after 2020. So, exponent of 30. Always check the context of the problem. Because if you actually type in the year 2050 here, that's 2050 years after the year 2020. That's much later than what we want. So, let's type it in. 4.6, 1.013, exponent of 30. We're looking at about 6.7771 million people. So or 6,777,100 people. All right. So what I'd like you to do is try example 3 on your own. See what you can come up with on example 3. Example 3 might also be decay instead of growth, but it's the same idea that we just did right up above. By the way, this example right here is something that companies actually use. Silas, you said that your family owns a company, right? You said your family owns a company? You said your family does? Like, what kind of company is it? Does he do like, he has equipment and stuff like that?
Yeah.
So I'm guessing he has to, like, when he buys new equipment, he probably does something called amortization. Where like he calculates the cost of the new equipment and then basically is able to write off a certain amount based on its value year after year after year until he knows when he needs to buy new equipment. That's what this is right here. That's what we're doing on this problem. So like as you use equipment and as equipment ages, it becomes worth less money over time. And so at some point that equipment needs to be replaced. So there's going to be a point where the amount of money that you gain from it is going to be less than what you're putting into it to keep it running. And so at that point, it's a good idea to go out and get new equipment. Anybody here do farming at all? Farm equipment, stuff like that? Like that's a big deal in farming as well, because farm equipment is expensive to buy and it's expensive to operate. And as things get older, you might know that like support in terms of like parts production and stuff like that, replacement parts goes away after a while as well. And so if you can't find parts for something, you're gonna have to replace it anyway. So, and you want to know maybe how much money you can sell it for. And so you have to basically talk about the depreciation of that particular asset to figure out how much use you can get out of it before you need to replace it. So here we go. A factory purchased a 3D printer in 2022 for $35,750. That must be a nice 3D printer to cost that much money. I mean, it's a factory too, so they're like doing manufacturing stuff. A lot of stuff these days, production-wise, is actually made by 3D printing. So that's gotten a lot more popular. The value of the printer depreciates every year by 22%, meaning that it retains 78% of its purchase price for each year that passes. This is the decay rate. That is the rate of decay. Kind of like the growth rate wasn't 0.013, it was 1.013. If something loses 22%, it still retains 78% of the initial value. So like if something costs $10,000 and it lost 22%, after 1 year, it's still going to be worth $7,800. So you would multiply that 10,000 by 0.078 as opposed to 0.022. Does that make sense? So you're not trying to figure out how much money it lost. You're trying to figure out how much it's still worth. You're not trying to figure out how many people were gained every year in the population. You're trying to figure out how many people there are in the population. So there's a difference between the growth rate and the growth factor. This is not the decay rate. Sorry, that's the decay factor. There's a difference between the rate and the factor. The rate is how much something is increasing or decreasing by. The factor is how much of that thing you're going to end up after you apply the calculation. Yeah. All right. So we're going to write a function here. So here we go. F of x, or I guess, how about this? 3D printer, what do we want? Value, v. Let's go with v for value. The value is equal to the initial purchase price. What was it? $35,750 multiplied by the decay factor, which is I should have said 0.78. 0.78. In terms of x, so it tells us to use x for the number of years. So we're going to say x instead of t. There we go. That's our function right there. V equals 35,750 times 0.78 to the power of x. All right. What's the value of the printer after 3 years to the nearest dollar? So we're rounding to the nearest whole number. Go ahead and type it in, figure it out. 35,750. I'm just going to write in the entire function here, 750 times 0.78. 3 years later would be an exponent of 3. How much is it worth in 2025? Because that would be 3 years later. Yeah, what's it worth?
16,965.
16,965. Good. Great. So it is worth $16,965 after 3 years. Before you do the calculation for this next one, does anybody have any ideas about what the answer is going to be? Hopefully it's not too hard to reason before we actually calculate it. Maverick?
Because it'll be the first 3 years.
Yeah.
50,000 number figure and percentage.
Yeah. You lose a lot more money if it's worth more money. If you have a decay factor, it's losing money pretty quickly that way. That's why, I mean, this has to do with cars as well. You will hear lots of people to tell you to never buy a brand new car. Do they give you a reason for that? Yeah, most of the value of a new car, if you buy a new car, most of that value is lost. You lose the most value on a new car purchase probably within the first 5 to 7 years. After 5 to 7 years, the value still continues to decrease, but the decrease is slower than it used to be. The depreciation is the most when something is new. So it's definitely going to be the first 3 years, but let's figure it out. So first 3 years, loses, let's see, 35,750 minus 16,965. So it loses $18,785 in the first 3 years, or more than half its original value. That's a lot, which means it can't possibly lose more money over the second 3 years because it doesn't even have this much more to lose, right? If it had that much more to lose, it would be in the negatives, which isn't a thing when it comes to value. So there's no way it could possibly be the second 3 years. In the first 3 years, it loses $18,785. In the second 3 years, it's going to lose, let's see, 16,965 times 0.78 to the power of 3. So we just use that same function again, but our new value is 16,965 as opposed to 35,750.
Can you use the same 86?
You could do that, but we want to know how much it lost. Well, I guess you could, and then just find the difference between the first 3 loss and the second 3 loss. Yeah, you can do that. That's fine. 0.78 power 3. Yeah, there's a couple ways to work that out. But after the second 3 years, the value is going to be $8,051, right? After 6 years total, $8,051. So after the second 3 years, it's going to lose another, what, $10,730-ish. Okay. So 18,785 minus 8051. Second 3 years loses $10,734. So yeah, it loses $8,000 more. There's $8,000 more depreciation in the first 3 years than the second 3 years. Cool. All right. Everybody good with the calculation so far? Feeling all right? Okay. Again, this is probably stuff like calculations and things. I don't think this is going to be brand new type of stuff that you've done, but if it is, hopefully you're following along okay. Anybody need more time here? All right, flip the page. Let's see. We're getting close. So, by the way, this is what we just used. Anytime you're talking about exponential growth, the growth rate, you always add 1 to it, and that gives you the growth factor. That's the value of B. Whatever the rate is, add 1 to it. If it's growth, if it's decay, take the rate away from 1, and that'll give you the decay factor. That's exactly what we just did on the previous page. So we just use those two. And if you want to, might be a good idea if you have a highlighter. Those two equations are going to be pretty useful. All right. And we just use those two, by the way. A is the initial value. The growth factor or the decay factor uses the rate. All right. Interpret an exponential function here. So since the function 24, y equals 24 times 0.8 to the x can be used to model the value of a car in thousands of dollars x years after it was purchased. We just talked about that. Does the function represent exponential growth or decay? Decay. All right. So circle decay. Or it just says down here, b is 0.8, b is less than 1, so the function represents its exponential decay. The decay factor is 0.8. What is the decay rate? What's that? That's the decay factor. 0.2, yeah. The decay rate is whatever gets this number equal to 1, which is 0.2. So decay rate equals 1 minus 0.8, which equals 0.2. So the decay rate is 0.2. What does that mean? Yeah. So this means the car loses 20% of its value every year. That's what that means. It loses 20% of its value every year. The decay factor means that it retains 80% of its value after every year, but that means it also loses 20%, which is the decay rate. Let's see. Graph the function on a reasonable domain. What do the y-intercept and the asymptote represent? When will the value of the car be about $5,000? First of all, we don't need to worry about graphing this one. Let's just take a look at the actual equation on our graphing calculators. And then let's just talk about part C, because I think we kind of understand what's going on here. So let's have ourselves a look. By the way, if we plug in 0 for x, what is the y-intercept going to be? 24. Okay. So what does the y-intercept represent? Okay. In terms of the actual problem, though, what does that represent? The initial value, which is what? $24,000. Yeah. Because it says it can be used to model the value of the car in thousands of dollars. So if x equals 0, y equals 24, which represents the purchase price of $24,000. So the car was a $24,000 car. All right. Again, I'm not too interested in like writing this down right now, but we can talk about it. What's our asymptote going to be? I don't see a plus or a minus after this function. So what's the asymptote? 0. Okay. What does that represent? What's that? Yeah. And it won't ever actually reach that. So the asymptote means that the car will always have some value, right? The asymptote is at 0. The car will never actually reach a value of 0, so it'll always hold some value. All right, last question here. When will the value of the car be about $5,000? So like for what value of x will give us a y value of 5,000? So let's look at the graph for that one. We're going to get 24 times 0.8 to the x power. Oops. 0.8 to the power of x. And we'll take a look at our table of values. And so we're looking for a value of 5, by the way. $5,000 would relate to a y value of 5. So a y value of 5 represents an x value of 7. Because the value would be $5,000 when y is equal to 5, which has an x value of about 7. So how long is it going to take for the car to be about $5,000? About 7 years. Yeah. All right. So is everybody cool interpreting this kind of stuff and working through these kinds of questions? Again, I'm sure you've done stuff like this in your science classes before, probably plenty of times. All right. Tell you what, let's skip it. Let's skip the one at the bottom of this page because I feel like it's something that is understandable here. All right, last example. A museum purchased a painting and a sculpture in the same year. Their values are changing exponentially as shown. So the value of the sculpture is here, the function. The value of the painting is here in graphical form, but no function for it. So this one says, identify the key features for the sculpture. So what do we know about the sculpture? Yep. So cost $50,000. Okay. What else? What's the growth factor? Yeah. Growth factor is 1.075. Okay. Now over here, we're going to have to find the growth factor for the painting. So the growth factor for the painting off to the side here. The growth factor B, take a look. I'm actually going to go ahead and put a blue highlight around this box because this is going to tell us how to do this problem. Because we already have the information we need for the sculpture, we need to figure out for the painting. So the growth factor B is the ratio between two y values when the difference between two of the x values is 1. So when the data are available, it's good to check multiple places. So
Then,
What's that?
40, 40, cost of 40 goes back.
40 and 1.1. Where do you see that? Down below? Yeah, we're going to calculate it though. Okay, so it says here, so we're going to find the growth factor for the painting and we're going to have 40 and 44. So there's information here. I think there's some information that we weren't given. Yeah, there is some information it looks like we weren't provided with. So there is a point on the graph that is, boy, that's really strange. Because we need a difference between the y values of x values of 1. So there's actually some information that we were not provided with, which is a little bit annoying. But if you have the values, so y2 and y1, so you need basically you need like the point 1 and then whatever the y value is after that, or you would need the point 4 years and whatever the y value is for that. Unfortunately, it doesn't actually give us those, which is annoying. I figured it should have. Yeah, the growth factor is 1.1, and I think Maverick saw that from the function down here. So yeah, and they purchased it. We know they purchased it for $40,000. We know that for sure because of the y-intercept here. But there's some information that should have been there that wasn't, which is irritating. But the growth factor is 1.1. So we should have, let's call this g of x is equal to 40 and then 1.1 to the x power. All right. So we'll call that good for today.